congruential arithmetic here. This involves a summation. Now, this reads the summation of the squares of the first 77 odd numbers. 2i plus 1 is the generic odd form, and that's squared. And so we're actually summing up the squares of the first 77 odd integers and verifying that that's congruent to 5 modulo 8. Now, just a little bit of a review on what we mean by modulo. If you think remainders, you'll be in good shape on this. If you look at this example right down here, notice that if you divide 15 by 8, you get a remainder of 7. Notice if you divide 23 by 8, you get a remainder of 7. 2 times 8 plus 7. Notice that if you divide 31 by 8, you get a remainder of 7. 3 times 8 plus 7 is equal to 31. And even 7 itself, you get a remainder. If you divide 7 by 8, you get 8 times 0 plus 7. So 7 is the remainder of all of these numbers, 15, 23, and 31 upon division by 8. And that comes in kind of handy. Also, another useful result is this guy right down here. It says if a is an odd number, we get that a squared is congruent to 1 mod 8. And you can treat congruences just like equalities in many cases. Now, this is kind of a quick little proof. Congruence means a squared minus 1 would be divisible by 8, or a multiple of 8. And if you look at the algebra that goes on here, that's exactly what happens. When you subtract these ones away from each other, you end up with 4i squared plus 4i. But notice this has to be divisible by 8, because one of these two numbers has to be even. If you have consecutive integers I and I plus 1, one of them has to be a multiple of 2, one of them has to be even. So you'll have 4 times an even number, which is going to at least be divisible by 8, and probably more depending on how far out you go out. So that's really a nutshell why this proof is true. Now, the rest of this is fairly straightforward. Each one of these numbers is odd. Okay, each one of these numbers is odd, and so it fits this criterion. Notice how I used the red 1 here. So you see, it really gets down to just adding up a bunch of 1s, which is very simple. You know, if you think about the size of this number, for I equals 1 right down here, for I equals 1, let me write, if you had for I equals to 77, and I'm just looking at one of the summands for I equals to 77, notice that we would have, that would correspond to 2 times 77 is what, 154? So you would have 155. You would have 155 squared, right? So look out, who knows, that's a large number, right? And that's just the last one. Again, for I equals 77, 2 times 77 is 154, I think, plus 1 is 155. And so just the very last summand would be difficult to reduce modulo 8. That's how powerful this result is. Now, how do we know this is equal to 5? Well, if you divide 8 into 77, 77 is equal to what, 9 times 8? 9, I'll put a dot there, folks, 9.8. So y'all, 9 times 8 is 72, and then plus 5, right? You see, this is what's so useful. That's where the remainder business is coming into play, you know? Just like, so 5 is the remainder here. 9 times 8 is 72 plus 5. And you can see how congruence arithmetic could really be called modular arithmetic. But anyway, 5 is the answer. I hope you enjoyed. I thought it was very cool to deal with these large numbers using modular arithmetic.